NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will prove a special result about the roots of a quadratic. Consider the equation ax squared plus bx plus c equals 0. As it approaches 0, show that one root goes to infinity in magnitude, and the other root approaches minus c over b. Before the algebra, let us build an intuition. We graph y equals ax squared plus bx plus c, and slowly slide it towards 0. Notice how the parabola flattens into a straight line, and one intersection runs far away while the other settles near minus c over b. Now, the first proof uses the substitution x equals 1 over y. Plugging in gives it over y squared plus b over y plus c equals 0. Multiply by y squared to obtain a plus b y plus c y squared equals 0. As it goes to 0, we get by plus c y squared equals 0. Or y times the quantity b plus c y equals 0. Therefore, either y tends to 0 or c y tends to minus b. Interpreting the two factors. If y goes to 0, then x equals 1 over y grows without bound in magnitude. If b plus c y goes to 0, then y approaches minus b over c, and x equals 1 over y approaches minus c over b. A second proof uses the quadratic formula. The roots are negative b plus or minus the square root of b squared minus 4ac, all over 2a. As it goes to 0, the plus branch can form the indeterminate 0 over 0. We rationalize with the conjugate to evaluate its limit. Taking the limit now is easy. As it approaches 0, the square root tends to the absolute value of b, so the expression tends to minus c over b. The other branch over 2 blows up in magnitude, giving the infinite root. Conclusion. We have shown, first by substitution, and then by the quadratic formula, that as it approaches 0, one root of ax squared plus bx plus c equals 0 diverges in magnitude, while the other approaches minus c over b. In this example, we study a parameterized quadratic equation and ask, for which value of m does exactly one root tend to infinity? Here is the key idea. For a quadratic ax squared plus bx plus c equals 0, if the coefficient approaches 0 while b stays non-zero, then the equation becomes almost linear. In that case, one root flies off to infinity, and the other root approaches negative c over b. Let us match coefficients. I equals m squared minus 1. b equals m squared minus 5m plus 4. c equals m plus 10. For one root to go to infinity, we need a to approach 0. So m squared minus 1 approaches 0, which forces m to approach plus or minus 1. But we also must keep b non-zero, otherwise the nearly linear idea breaks. Evaluate b at m equals 1. That is 1 minus 5 plus 4 equal to 0. Reject. Evaluate b at m equals negative 1. That is 1 plus 5 plus 4 equal to 10, which is non-zero. Accept. Therefore, exactly one root tends to infinity when m approaches negative 1. The other root approaches negative c over b at m equals negative 1, which is negative 9/10. Visualize m sliding toward negative 1. The coefficient at equals m squared minus 1 crosses 0 there, while b stays safely away from 0. Final result, m approaches negative 1. m approaches negative 1. Final result, m approaches negative 1. Example, we will analyze a parameter-dependent quadratic and find the value of a such that one root tends to infinity. Step 1. Treat the expression as a quadratic in x with a as a parameter. For a root to blow up in magnitude, the coefficient of the highest power of x must tend to 0. Here, that leading coefficient is a to the 4th minus 1. So we set a to the 4th minus 1 equal to 0, giving it equals plus or minus 1. Step 2. For a quadratic px squared plus qx plus r equals 0. When p is close to 0 and q is not 0, one root behaves like negative q over p and therefore diverges, while the other tends to negative r over q and stays finite. So to get exactly one infinite root, we need p of a equals 0, but q of a not equal to 0. Step 3. Test the candidates. At a equals 1, p equals 0, but also q equals 0, so the condition fails. No infinite root is produced. At a equals -1, p equals 0, but q equals 2, which is not 0. Therefore, one root scales like -q over p and diverges, while the other tends to negative r over q, which here equals 0. Hence, only a equals -1 satisfies the requirement. Final answer. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.